Hello everyone, thanks for attending my presentation today. My name is Jingfu Chen. I'm working on Huawei Technology Canada. This work is supervised by Dr. Wei Shang and Ima Shiha from Concordia University. Our work is about how to predict performance regression from tests at the commit level. First, let me introduce the background and the motivation of our work. Performance is a very important aspect of software quality. Prior study has reported that software system failures are often due to performance issues rather than functional bug. And performance is often measured by response time, CPU usage, memory, and I/O usage. Performance regression is one of the typical performance issues. Such performance regression may have financial impact on the industry. A report by Amazon shows that a page load slowdown of over 1 second could cause $1.6 billion loss. Another example is from Mozilla. Mozilla takes performance regression seriously. In their documentation, they mention that they cannot allow performance regressions to go unnoticed or unresolved during their development cycles. However, there is challenges in coping with performance regression. Many organizations all too often wait until the last minute for performance testing. The existing performance regression detection is too late. Large amounts of resources are required to detect, locate, understand, and fix performance regressions at such a late stage. Our prior study proposed to use the readily available tests from the release pipeline to detect performance issues. However, there are too many tests and too many commits to analysis. Running all the tests to detect performance regressions takes too long. Imagine that if we know which commits and which tests are more likely to be performance regression prone, we can already exercise those tests. We can already examine the source code covered by those kind of tests. Therefore, a smarter approach is needed. In this study, we want to predict tests that manifest performance regressions at the commit level. To do that, we want to build prediction models to predict which tests in the commit manifest performance regression. We first collect our performance data. We follow 4 steps to collect our data. First, we filter commits. We only consider the commits associated with source code changes. Second, we identify impacted tests. Each project may contain many tests. If we run all the tests, that will be too time consuming. After identifying all the impacted tests, for each impacted test, we evaluate performance by executing each test 30 times independently. With the performance results, we finally perform statistical analysis on the performance evaluation results to identify performance regression prone tests. Then we will build our models to predict performance regression prone tests. With the identifying impacted test, we extract metrics. Then we pre-process our data and finally build classifiers to predict a given test, whether a given test manifests performance regressions. In our approach, we consider both traditional software metrics and also performance-related metrics. Before using the extracting data to build our classifiers, we pre-process our data. We perform a correlation analysis and redundant analysis to remove correlated metrics and the redundant metrics from our collecting data. Finally, we choose 4 different classifiers to predict whether a given test manifests performance regression. We choose 3 open source projects, Hadoop, Cassandra, and OpenJPA as our suggest system. We spent a total of 133 machine days collecting our performance regression prone tests. we first want to know how well can we predict performance regression from tests. We found that our classifiers can accurately predict performance regression from tests, despite the fact that they are very rare. And we found that our random forest achieve the best performance. Our random forest classifier can achieve an average AUC of 86% when predicting performance regression from tests. However, performance evaluation is still time and resource consuming task. A designable prediction result should predict performance regression from test and also minimize the needed time to execute the test. Therefore, we measure the actual performance testing time as a cost factor for each test. We build three models to prioritize the performance regression test. In the optimal model, we sort all the actual performance regression from tests by their execution time. So for example, the sorted test that manifests performance regressions should run first. Then we build a cost-aware prediction model by also considering the execution time of each performance regression from test. Finally, we use the model from RQ1 as our non-cost-aware model. It solved the probability of being performance regression of each test. In this research question, we use the cumulative lift chart to evaluate our models. The lines in this chart demonstrates that by spending how much time to execute tests, how much more performance regression from tests can be evaluated. We found that our cost-aware models have high cost effectiveness and close to the optimal model. In particular, using the top 5% of the total cost, we can cover 15% to 63% of all the performance regression from tests. We also want to know the practical impact of our approach. We collect all the real-life performance issues that are reported after the first commit of our study period from our subject systems. We then label each performance issues into different kind of performance metrics. Then we use existing evidence to detect the performance issues introducing commit. And finally, we examine our prediction results to see whether our approach can be used to detect the real-life performance issues. We collected a total of 9 performance issues, and we found that our approach can be used to detect 6 out of 9 real-life performance issues. We also manually examined the 3 issues that are not successfully predicted by our approach. We found that one of the issues has a performance regression probability with 0.49, which is very close to our threshold. And the other 2 issues are rather complicated performance issues like deadlock, which are expected to be difficult to capture using our static matches. And finally, we want to understand the influential factors of the performance regression from test. We use the variable importance value that is calculated from the random forest classifiers. Finally, we found that the traditional metrics are more important than the performance-related metrics. And the histories and the size dimensions are more important than other dimensions in the traditional metric. Such can give the guidance for the practitioners when they want to detect the performance regressions. They should care more about the history and the size dimension metrics. But that's all my presentation. Thanks for listening.
All right, so we should be live. Thank you, Jinfu, for your presentation. It is now time for question and answer. So I suggest the 36 attendees in this session to ask questions to Jinfu by using the chat system. I can see already that Amir has a question for Jinfu. The question is, how is the balance between the two classes? Yes and no. Also, did you try other binary classifiers such as SVM? So the first question is about how much the dataset was balanced, and the second one is why you used the random forest and not other classifiers somehow.
Okay. Yes, thank you for the two questions. And actually, when we collect the performance regression data, is highly imbalanced. Then, actually, in our experiment, we try to use some rebalance techniques like unsampling and also the smooth to try to keep our data, make our data balanced. And finally, we found that the rebalance techniques, they are not able to improve the performance of our prediction. And for the second question,
I have
actually,
a follow-up question
yes.
before you ask. Was it balanced? Was it over-balanced towards the yes or towards the no? You probably had less bugs, right?
Oh, yeah. The yes label is much less than the no label. It means, yeah.
Was it about 10%, 5%, 1%? Do you know how much was it, more or less? Do you have
Actually,
any
in
idea?
our three suggest systems, I see, yeah, what I remember is that I see the regression data all are less than 10%. I think the average percentage is about 3 or 4%. Yes.
This makes the job very hard for a classifier, of course.
Yeah.
Okay, how about the second question? So did you try other binary classifiers such as SVM?
Yeah. Maybe, yeah, because the time limitation, we always show the random forest in the slides. Actually, we try different kind of prediction models, including the registered regression model, and also, yeah, we also include the SVN, and also we include the XGBoost. And finally, we found that in most of the performance metrics in our suggest systems, and we found that the random forest achieved a better performance than other classifiers. And finally, in other research questions, we choose to use the random forest.
Okay, so we have another question from Frolin. The question is, most of the tests written in practice are written primarily with functionality in mind instead of performance. If developers started writing more tests that specifically consider performance, like running a function with large input to assess scalability, do you think that that will benefit your approach, or are functional tests sufficient?
Yeah. Actually, yeah, I agree of this. Uh, Actually, in this paper, we use the readily available functional test as a small test to evaluate the performance. We run the functional test 30 times independently. We choose this kind of test because they are maintained and they are run in a daily basis. And for the other point, since do you see? Yeah, I think it will be benefit for our approach if the learning a function with large inputs to assess scalability. Yeah, I think it will benefit for our approach.
Uh-huh.
Uh,
Okay.
yeah, actually we have a paper in XC 2020 and we summarize the reasons and some kind of the patterns why the functional test they can or not detect performance regressions. And yeah, if
Mhm.
if the audience is interested in this, maybe you
Yeah.
can refer to our paper.
Yes. So my question is that you have tried this approach in 3 open source projects. Do you know what will happen if we try it in industry? So of course it's just a speculation, but do you think that it will scale? It will work anyway? Or maybe a better question is, what are the preconditions for this approach to succeed? What do you need? Do you need a large code base? Do you need a lot of test cases? Do you need a lot of coverage? Do you need a programming language?
Okay, yeah, this question is very good. Actually, if we try to transfer our approach to the industry, I think the first requirement is the number of the test, right? We need to have the maybe maybe a large number of the existing uh, benchmark or like the high quality functional test, then we can use this kind of test to detect the performance. And another thing is that, yeah, like I mentioned before, the quality of these tests, they are very important. If these tests, they have the high coverage,
Of
then
course.
that will be more useful in our approach. And and I say another one is that maybe and also the code chunks in each commit, because our approach is at the commit level. And if a commit, I mean, if the code chunks is very small, maybe our approach is not very useful for the industry. Yeah.
Okay.
Yeah. So yeah, basically we need uh, the high quality test, and they have the higher coverage on the code change, and we also need some historical performance data. Yeah, that's our requirement in this approach. Then we can transfer our approach to the industry. Yeah.
The other question is that I have, Jinfu, is about how do you define somehow a performance bug? So if you have a tolerance level, or if you just look at the spike of what is going on, so a spike is a bug, or if you have, like it is for unit tests, that you have an expected value. If that value is not equivalent to the expected value, then it's a bug. And you also in unit tests, you can have a tolerance level. So does it work like this, or how does it work?
You mean, yeah, maybe I can repeat this question again. Okay,
How you define a
define
performance?
a performance bug?
Yeah.
Uh, I think, yeah, performance bug actually in the traditional way, performance bug is defined. So assume that we have two versions of a system. Then for the same feature, if the performance like the response time or the CPU usage, memory allocation, or the I/O usage, network connection, if they are worse than the older version, then we can say that there is this performance bug in the new version. Yeah. Then if for the performance bug detection, like in a traditional way, we can just use some statistical techniques like the control graph or or other kind of statistical test like the t-test or mean test to compare the performance data between the two versions to identify whether they have the performance bug.
I
Yeah,
see. All
that
right.
is okay.
All right. So I can see there are only 15 seconds remaining. So I thank Jin Fu for the interesting answers. And we will now be ready to move to a discussion room that will be available with a pop-up. So thank you very much, and have a good rest of the day.